There's some really complicated versions of this. Probably the most complicated one you're going to come across is finding the maximum range of a projectile, which is a question you will have been set in one of your sheets. I just want to show you the basic way of finding the maximum value that something will reach using calculus. It's an idea you'll have come across in maths, and we're not going to do anything new except to just, as usual, do it in the context of a physics question. So what we're going to suggest is we've got a displacement of an object, and the displacement of the object changes with time according to this relatively simple equation. So whatever it's doing, this object is 100t minus 3t squared meters away at any given point. Okay, so in order to find the maximum or minimum distance that it would travel, in this case it's going to be a maximum, but depending on the type of equation you've got, you might be finding a minimum value instead. Okay, so very simply, the first thing you do is find the first differential. You solve it. This basically gives you your answer. But then you just need to find the second differential. And what this does is it determines if your answer is a position of a maximum or a minimum. Now, in the example I'm going to work through, there is only really one answer that's of any significance. There is a second answer, and we'll talk about what that means in a second. So this is a little bit more straightforward to do, but the process is exactly the same, even if this is more complicated. It's just that the maths you end up doing is a little more complicated. So let's take the first differential with respect to time, ds by dt. Now, I also know that this is telling us something else, incidentally. I know that this is telling us velocity, but this isn't the velocity function. I'm using this because I want to know this as the gradient function. If you think about it, and you'll have learned this in maths, if we plotted the graph of displacement against time, it's going to go up and it's going to then come back again. So what we're looking for using the graph, something like this, say, is the point where it gets to its maximum. So what I want to know is when does it reach its maximum distance, and I can also figure out how far does it get. Now, at that maximum point, it's reached what we call a stationary position. We know that the line is flat at that point, so we know that the gradient is 0. Now, that happens in 3 cases: when it's at maximum, when it's at a minimum, and when it's at an inflection point. An inflection point, remember, is something that looks a little bit like this. That's an inflection point. It's a sort of false reading if you're after a max or min, because as you can quite clearly see, it's neither a max or a min. Sometimes you can have functions that look a little like this, and you can have local maxima and minima, but it's not actually a overall maximum minima. If the function you've got is only valid, let's say, up to this value of time, or whatever's on the x-axis, then this would be a maximum, and that potentially would be a minimum, and that would still work out. Either way, the process of finding these is no different. So, although the ds by dt gives us velocity, that's not what I'm after it for. I am after it for the gradient function. So, ds by dt for this is just going to be 100 minus, so multiply by the power, drop the power down by 1, 6t. The gradient function ds by dt at this point is going to be 0, so that's why we solve it, place it equal to 0. So 100 equals 6t. So the time at which it reaches a inflection point, whatever that might be, is 100 over 6. I'm going to leave that as a fraction, just so I don't introduce any rounding errors, because it's not a horrible fraction to have to deal with. Okay, yeah, we could obviously round that down a little bit. 50 over 3 if you wanted. So we have found the first differential, we've solved it. What we can do is also now find out what the actual displacement would be. So the displacement when t equals 50 over 3 is 100 times 50 over 3 minus 3 times 50 over 3 all squared, which we just shove that into a calculator for a second, gives us 2,500. I'm assuming this is all in meters and seconds, although they haven't really specified that. So S would be 2,500 meters. So that's an answer. I know that's a maximum or a minimum distance that it's travelled. Now, I could sketch out the function roughly as to what I think it's going to be, and I could sort of determine from that sketch of the graph if this was a maximum or a minimum, or if there's likely to be multiples or likely to be inflection points, in which case I can kind of determine from that this is going to be a maximum. But to use the full calculus method, what we do is we take the second differential. d2s by dt squared. So again, we're taking the second differential of this equation. So the 100 now disappears, and I'm just left with minus 6. And we have to interpret the answer. So there are 3 interpretations of the answer. If the second differential is if it is positive, the interpretation is that we found a minimum, or at least a local minimum. If it is negative, then we found a maximum, or again at least a local maximum. If it is 0, then we found an inflection point. Now, the only complication you might find here is that this could be a function of time. So if that's the case, what you've got to do is put your time into it and see whether it comes out positive, negative, or 0. Obviously, this is minus 6 no matter what the value of time is, so that's not going to make any difference. For me, this is a negative, so therefore S equals 2,500 meters is a max distance. That's my check done. You can do that for anything you have the equation for. It doesn't matter what it is, you can find a maximum points. Now, the only problem with what I've done here, and hopefully the eagle-eyed mathematicians amongst you will have spotted it, is that there are 2 solutions to this equation. We also have to just consider, to the S equation, we do have to just consider what happens when S is 0. So we do get, obviously, 2 solutions to that. T is 0 and T would be whatever T the solution is. So you do just need to be a little bit careful at this point when you are solving your gradient function here, how many solutions there are. Now what we've got here is a linear function. So there is only one solution, that's not complicated. But if there are multiple solutions, what you've got to do is do the second step, finding the second differential, and then determine if their answer is max or min for each of them. When you've only got one solution, that's not a problem. But if this was a quadratic or had multiple solutions, you've got to check each of them. There might be more than one max or min, or it might be that one of them is an inflection point, but it's easier if you know what each of them is. If it gets very complicated, then you possibly find out it's a good idea to sketch out the function, so you've got a bit of a visual of what it is. But at this stage, we're not going to ask you to deal with anything quite that complicated. We'll be sticking mostly to simple polynomials and just local maxes or mins, and that's all you'll really have to find at this stage.